K becomes, the closed loop system becomes unstable. So that's the whole point of root lookups. It basically gives us some branches that shows how the poles of the closed loop system move as K, which is the scalar in the loop, changes from 0 to infinity. Okay, so this is one example that shows the root lookups. Now I'm gonna erase this, and I'm just gonna provide some rules that you should remember when you want to draw a root locus. Okay, I'm not gonna prove them for you. It's like some of them are not very straightforward to prove, and it's not the scope of the course to prove them, but it would give you some insight into stability of systems, so it's good to know. So the first one we already saw number of branches of root locus is exactly equal to the number of closed loop poles. Each branch starts, where does it starts from? Starts at poles and ends at zeros of GS, GHS, right? We saw that before. Another rule, there is always symmetry with respect to real axis, the horizontal axis. Number 4, which is, this is something that you saw before. So this is what we had before, but let's take a look at this rule. Root locus branch exists on the real axis to the left of odd number of zeros and poles. What does this mean? Okay, so we knew that our root locus branch, it's gonna start from here and ends here, right? But this rule, it tells us that there is gonna be a branch on the real axis to the left of odd number of zeros and poles. Okay, so we have only 1, 0, 1 pole. So at this point, on the right of this, like here, right here, we have 2 poles and zeros on the right side. So like we don't have any root locus branch here. Over here on the right of this, we don't have any poles and zeros. Again, like we have 0, so it's even. But anywhere here on the left, so it says like real root locus exists on the real axis to the left of odd number of zeros and poles. So we have only 1 0 here, so that to the left of it we have a root locus branch. Okay, this one is not that difficult to prove because we can just like again use this formula basically to prove it, but I'm not gonna prove it here. But like if you guys wanna do it, like you can just like use this formula to prove it, because any point here would satisfy this, but any point here would not satisfy it. Any point here would not satisfy this. Number 5, this one we are only going to use it in special cases. but it's very good to know. Root Lucas approaches a straight line, so it will be a straight line asymptote as k approaches infinity. So I'm gonna explain these two formulas a little bit later, but it's gonna happen at these 2 points and this angle. So let me just like write the formula down, and like using one example I'm gonna show what this means. Finite poles minus summation of finite zeros divided by number of finite poles minus number of finite zeros. And it's gonna happen with the angle of 2k plus 1 pi, the same denominator, number of finite poles minus number of finite zeros. Okay. This one is a little bit challenging, so I'm gonna explain this one using an example, but let's just like go over the first 4. So number of branches, it's gonna be always equal to number of closed loop poles. Always starts from a pole of this term and it ends at a 0 of it. The root Lucas is always symmetrical with respect to the real axis, the horizontal axis. There is a root Lucas branch on the real axis to the left of odd number of zeros and poles. Root Lucas would have a straight line asymptote as k moves to infinity. It's gonna happen at this point and with this angle. Okay, so let's just like explain these rules using examples. In the exam I'm gonna ask like very simple cases, but the examples I'm doing here, it's gonna cover all different scenarios. So let's just focus on the first example. I give you GS GHS is equal to S plus 1 divided by S minus 1 times S plus 2. Okay, and we want to draw the root Lucas of this to find the closed loop poles. So real, imaginary. Okay, maybe I should do this one more time. This is K.